All right, so here I want to deal with applied questions dealing with exponential growth and decay. So I'll start with this statement here. If the amount of something, A, exhibits exponential growth or decay over time t with some constant relative growth rate, R, the rate of growth, or rate of decay, it can always be modeled with this function. So anything that grows exponentially or decays exponentially can be modeled with this function, where A, again, is the amount after some time t, E is the Euler's constant, and R is the constant relative growth rate. That's the phrase, the rate of growth, rate of decay. Okay, so I want to show you, if we take this equation and we differentiate it with respect to t, what we get to. Okay, so what I'm doing, as you can see, is differentiating both sides with respect to t. Now if I do that, the left-hand side just becomes dA dt. The right side, keep in mind, I'm differentiating with respect to t. So that means there's t. That means all of this here we can treat as a constant. You know, the initial amount's a constant, E is a constant, R is the constant relative growth rate. So we're differentiating with respect to t. With that said, we still have a linear function, R times t, inside an exponential function. So we have to use a chain rule. But remember again, R is a constant, where R is the constant rate. And so using the chain rule, I differentiate the outside part first. So the derivative of exponential function, the base of e, is unchanged, times the derivative of the inside function. But again, the inside function is a linear function because R is a constant. And the derivative of a constant times t, or the derivative of a linear function, is just the same as its slope. And so all of that there you see in red is just the same as R. The d dt of RT is just R. And so at this point, I can take all of this here, because everything I'm highlighting in blue, notice, is the same as A if I go back to the start. A, the amount at some point in time, is the same as A naught times e to the power of RT. Well, A naught times e to the power of RT is what you see here, so I'm going to substitute that back with just A. Again, that A represents the amount at some given time. And we get this very nice, simple equation, what we call a differential equation. And so the derivative of any exponential function at some point in time is the same as the amount at that point in time times this relative growth rate. And so any exponential function can be, at some point, expressed in this form. Now we notice this equation, it has a derivative in the equation. And so we call this a differential equation. But it's a pretty simple equation. The derivative, dA dt, is the same as the amount at some point in time. Again, that's not A naught, it's A, which represents the amount at some point in time, times this constant rate of growth. So again, this is called a differential equation. That's because we're defining a relationship using a derivative. So essentially, when dealing with exponential functions, quite often they're defined in this form going forwards, defined as a derivative. Because in many ways, that equation there is simpler than this equation up here. Okay, so let's look at a few examples. And a common application of exponential growth involves the growth of some sort of population, which can be quite accurate over at least periods of time. So the world population grows proportionally as a function of time in such a way that it satisfies the differential equation we see here. dp dt equals 0.011 times p. So the first key is, what on earth is this telling you? I am defining the growth of the world population with this equation, which is a differential equation. That's it. That probably seems a little unfamiliar. So my first question is, what is the constant relative growth rate? And again, look, going back here, the constant relative growth rate is what we call the R here. I've been highlighting it in green. So what's the constant relative growth rate here? It's the constant multiplied in the, or I should say it's the constant coefficient in this differential equation. So 0.011 is the constant relative growth rate of this particular function. So what does it represent? so the 0.011, this represents the instantaneous rate of growth of the world's population at any given point in time. And as a percent, which we don't have to express it as a percent, but quite often we do, that's 1.1%. So this represents that at any given point in time, according to our model, the world's population is growing at a rate of 1.1% per year. And don't think we have to express it as a percent, but it's kind of natural to. So essentially, if the world population right now is pretty much 8 billion, according to our model, 8 billion times 1.1%, that'll tell us, as of right now, how the Earth's population is changing. But if you went back 100 years to when the world's population was between 1 and 2 billion, let's say 2 billion people, 1.1% of 2 billion would be a lot less. And so at that point in time, the world's population was growing at a slower rate. So please don't mix up constant relative growth rate with constant growth. Constant growth is linear, but again, exponential growth is quite different than linear growth, but the growth rate is constant. So with that said, if the current population is about 7.5 billion, use this differential equation above to predict the world's population in the year 2000. Okay, so how can we do that? Well, one key thing to realize is that anytime we see an equation expressed like this, if we want, we can express it in this form. And any equation we see written in this form, we can express in this form. And so for this particular question, I really want to express this in the other form. So I want to express this using that sort of A equals E, A naught times E to the RT, but I'll use population here. So this equation that I gave you at the beginning, we can write as P equals P naught times E to the RT. In this case, R is about 0.11, or actually it was given to be exactly 0.11. I'm telling the initial amount is, we'd say, is the population right now, so 7.5 billion. I'll just write 7.5 times E to the 0.011 times T. So what am I going to put for T? Well, if I'm calling 7.5 the world's population right now, and let's say it's the year 2020, and so that would be negative 20. Now, to be honest, I'm actually writing this at the very beginning of 2021, but I like the number negative 20 because it's kind of a nice clean number. That's it in the end. I could simplify this down to 7.5 times E, 0.011 times negative 20. I could calculate, I could put that into, I could decimalize that, but you know what, I'm not going to. Honestly, what I have right there is the most important part. If I were to decimalize the whole thing, though, using a calculator, I get about 6.02 billion people. Which is actually pretty accurate. And in the year 2000, the 6 billion is actually quite accurate. So this model of the world's population, how the world population is growing, which again was originally expressed just like this. It was expressed as a differential equation, is fairly accurate as long as we stick to time periods somewhat close to we are now. Obviously, if we try to extrapolate a few hundred years into the future or a few hundred years in the past, it probably gets less and less accurate. But remember again, the most important part is understanding what this original differential equation represented, and how in this case, for this, I can always express it like this if I want as well. They're all connected, because that's really the very first thing I showed you, is algebraically how these two forms are connected. One has a derivative, one doesn't. Okay, one more question about this. If the current population of the world is about 7.5 billion, use the differential equation above to predict the growth rate of the world's population in 2000. So in the year 2000, what was the growth rate of the world's population? Now you may want to say 1.1%, which is partially there, but 1.1% of what? In the year 2000, how quickly was the world population growing? So 1.1% of what? And so for this, I'm asking for a derivative. I'm asking for the rate. So I want to go back to this, dp dt. I'll go back to this form. And again, this p represents the population at some point in time. Well, that said, I want to find the rate of growth in the year 2000. So I want to pick p to be the population in the year 2000, which we know from the last question was about 6.02. That's the population in the year 2000 according to our model. And so all I need to do is multiply that by the constant relative growth rate, 1.1%. And I get, in this case, 0.066. Now the units are billions of people per year. And again, if you're ever unsure about the units, again, look back at your derivative in this form. And look at the derivative for p. The derivative of p was billions of people. The units for t was years. So 0.066 billion people per year, which is a little more, I think, easier to understand if I write it in millions. So about 66 million people per year. And if I just picked some other year, found the population then, it would tell me the rate at that point. Which again is really quite simple. It's just 1.1% of the population at some given point. And so we don't want to lose sight of the fact that this differential equation here is a very simple equation. Doesn't mean all the questions will do with it or will work with it simple, but it's a very simple equation, which is actually quite pleasant to deal with, simple equations like that. All right, let's look at an investment. So if an initial investment of A0 grows at 5% interest and it's compounded continuously, the value of the investment after t years will always satisfy this differential equation, where again 5% is my constant relative growth rate, A is the amount of money at some point in time, and so this equation will always be true for this scenario here. So say I invest $100,000 in an investment that grows at 5%. Compounded daily, but for the sake of simplicity, let's say it's compounded continuously. If it's compounded daily, then this equation here is not quite correct. But as we've seen earlier in the course, when you start to have this many compounding periods, we actually had questions just like this where we compare the difference in something growing compounding daily versus compounding continuously. The difference is very, 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 very slim. And if we think about it compounding continuously, we can use this simple equation here and any variation of it. So that's what it says here for the sake of simplicity. Let's say it's just compounded continuously. So my question is, after how many years will you be earning interest at a rate of $10,000 per year? Okay, so you have $100,000, it's growing at 5% interest, compounded continuously. When will that investment be growing at a rate of $10,000 a year? So for this, again, anytime I have an equation written in this form, if I want, I can write it in this form as A equals A0 times e to the RT. And again, R is 0.05, so I'll just change that right now. And my initial amount is 10,000. So actually, I'll just change that as well. All right, so if I want to find the rate it's growing at $10,000 per year, let's differentiate this. And so I can differentiate this quite easily. I have to use the chain rule if I differentiate it, though. So when I use a chain rule, I'd go 10,000 times 0.05. I'll just do that right away and get the 5,000. E to the 0.05 t times the derivative of the inside function, which is 0.05. Because the inside function, again, is a linear function. Oh, sorry, I screwed up. And I'm too lazy to re-record everything before. Let's go back in time a moment. If I differentiate this using the chain rule, first I want to go 10,000 times e to the 0.05 times t. That's the derivative of the outside function times the derivative of the inside function, which is 0.05. And now, 0.05 times 10,000, or times 100,000. Oh, so many screw-ups. Take 3. So 100,000 was the initial amount, right? Yeah. So take 100,000 and times by 0.05. That's where I got that 5,000 from. Times e to the 0.05t. Okay, took me a few screw-ups, but such is life. And again, this is my derivative at some point in time. All right, so now I'm trying to find how long it takes till this derivative is worth 10,000, till it's growing at $10,000 a year. And so I'll change this to 10,000, and then it's a matter of just solving this exponential equation. And hopefully I do that without screwing up. Divide both sides by 5,000. I get 2 equals e to the 0.05t. Put this in logarithmic form. I get the ln of 2 equals 0.05t. So t equals the ln of 2 divided by 0.05. Which, if I were to decimalize it, I get about 13.86 years. Now, I will say, you may wonder why, since I was trying to find when the derivative was 10,000, you may wonder why I didn't work with this equation right here. If we look at this equation right here, the problem with this is, I know it's 5%, it's the amount at some given point in time. There's no time in this equation right here. There's dt, but there's no units of time. And eventually I'm trying to find time. Now, I'm not saying there aren't ways I could have done that. That was my sort of rationale for just changing it into this form here, because I don't want to change it in this form here. I have that unit of time that I'm eventually trying to solve for. But there's always other ways we could approach it. Okay, last question, looking at half-life. And so I start with a half-life curve for this iodine 131. All right, and we can see some details of it here. Time in days on the x-axis, the percentage remaining of this sample on the y-axis. So the first question is, I want to express the decay of this substance as a differential equation in this form. And so really, all I don't know here, what I need to figure out is R, the constant relative growth rate. So how on earth can I do that? Well, first let's put this, the find R, let's write this in the other form. Let's write it like this. A equals A naught times e to the RT. The reason I want to write in this form is I can now look at my graph and look at a couple of values, A naught being the initial amount, which honestly, I don't have to use the starting point of the graph, but I might as well, 100, and some other point. And so I just need to pick another point, and why not pick right there, 50, which is also the half-life. So for example, I can see, if I look at my graph, that after 8 days, there's half as much iodine 131 left, or the half-life is 8 days. I can just see that now from the graph. And so the half-life of 8 days is useful to me, because if I go back to this form, I know my initial amount, which I'll just say 100, let's say, will go down to 50, and I could skip that and just change it from 1 down to a half, but 100% down to 50%, and all I don't know the rate of growth, I do know that took 8 days. Now I can solve for R. And so again, divide both sides by 100, or you could just jump straight to the step. 1/2 equals e to the 8r. So the ln of 1/2 equals 8r, which means r equals the ln of 1/2 over 8. Which, honestly, I don't have to decimalize it, but if I do decimalize it, I get a negative number, negative 0.087. And that'll always happen when we deal with decay. When we have growth, your constant relative growth rate is a positive number. When it's decay, it's always a negative number. With that said now, I can actually answer this question here, to express the decay of this substance as a differential equation. So now I can take all of this here and write it as dA dt equals this relative growth rate. I'll put both the ln of 1/2 over 8 times t, sorry, times a, I meant to say, the amount at some given time, or I could decimalize it, negative 0.087 times a. That leads me, I believe, to the last question, which is now express the same function in this form. And so it should be quite quick now. A equals a naught times e to the, again, the ln of 1/2 over 8, all times t. Now, and as well, I could write this as a naught e, or I could decimalize it. Keep in mind, this is more of an approximation. And I could call a naught 100%, but again, that's not really something I'm too concerned about. I think that's it. All right, so before I end this, just keep in mind, most of this is really just about understanding what this equation here represents and how we can work with it. Going forwards in future calculus classes, you deal with differential equations a lot. I'm really just kind of introducing the idea here. So not a lot to look at.